Hi, everybody. Welcome to Unit 8. Unit 8 is another unit all about tests of significance. And so if you think about what we've learned with tests of significance, you learned a lot about z-tests, which test for proportions, either one or two proportions. You learned about t-tests, which test for means, one or two means. And now we're going to learn our last type of test, which is a chi-squared. I know it's spelled C-H-I, it's pronounced chi, square test. And there are three types of chi-square tests that we will learn. The first is called goodness of fit, and it allows us to examine the distribution of a single categorical variable for a population. Remember, categorical variables are variables that are words, not numerical. So colors of things, eye color, favorite class, favorite type of food, things like that. And so our first example today says the company that makes milk chocolate M&Ms claims the following distribution. So it gives us a distribution for colors for each M&M. And we want to know, is this distribution true? And so we observed a sample of 100 M&Ms and recorded the number of each color that were represented in our sample. And so this means the sample percent for brown was 16. Well, it was supposed to be 14 according to the claim in our sample. Percent for yellow was 12. Yellow was 14, brown was 13. So you can sort of see where we're headed here. Now, every chi-square test, just like every t-test and z-test, starts with a hypothesis. We would have both the null and the alternate. And the null will say that the claimed distribution is accurate. Okay, the alternate will say the claimed distribution is not accurate. All right. And so let's suppose that M&M's claimed distribution is correct. So this one up in the bold box. If they are correct, how many of each color would we expect to get in our sample? So remember, our sample had 100 M&Ms. And so if 13% of the M&Ms were brown, we would get 0.13 or 13% brown. 14% yellow, 20% orange, 16% green, 24% blue, and 13% red. Okay, and I just got those from here. And of course, I just used that nice even number for n as 100 just to make things easy. Now we have quite a process. So we have a table that we are going to figure out. And this tells us how we should calculate it. So if our expected value, this really should just be 13 for brown. We would have expected to get 13 brown M&Ms based on the claim distribution. We actually observed 16. And so when we subtract those, observed minus expected, I'm reading the header up here in my table. I have 3 more than I thought I would, which is 9 if I square it. And then when I divide that by the expected, I'd have 9 over 13. Okay, now we're going to do that for every color. So for yellow, we observed 12. We expected to see 14%, so 14. So if I subtract that, I get negative 2, which squared is 4. And then if I divide that by the expected, so observed minus expected squared is 4. Divided by the expected, that's 14. For orange, I would have observed 23 when I expected to see 20, because 20%. Subtract those, I get 3, so this is 9. So this will be 9 over the expected 20. Okay. Green, we expected 16. We actually observed 14. So this is also negative 2. So when we square that, we get 4 over 16. All right. Blue, if I scroll up here, blue, we saw 26. we expected 24%, so 24, 2, 4, 4 over the expected 24. And then finally red. Red, we observed 9. We expected 13%, so 13. 9 minus 13 is negative 4. Squared is 16, so this would be 16 over 13. All right, and so then to finish it up, we're going to add up this last column. So I'm going to plug all those fractions into my calculator. Remember, fractions are the exact number, whereas if we did 9 divided by 13 and ended up rounding, that would be a little less accurate. So we want to be as accurate as possible, so that's why I keep them as fractions. So 20, 4 over 16, 4 over 24, and 16 over 13. So we get this is where we are going to round, 0.755 if I go out 4 decimal places. All right, now that's our test statistic. So remember in the past we used a t-score or a z-score. This is our chi-squared test statistic. It's our chi-squared value. And so if our sample was very close to what was expected, then our observed values would be close to our expected values. And so this difference would be close to, if not 0. And so then this numerator would also be close to, if not 0, or a very small number. So that test statistic, if our sample was very close to what is expected, would be a very small value. However, if our values or our sample was very far from what was expected, so like here where we had 9 and 13, that was a pretty big gap. Well, then when you subtract, you get a big difference. When you square that, you get an even bigger number, and then you end up dividing it. So that creates a very large value. Now remember, we are trying to check to see, are the actual expected values or percents for that distribution similar to the observed values? Because if they are, then that's an accurate distribution. Then that is sort of proving that the null hypothesis is true. But if our observed values are very different than the expected, that might be evidence for the alternate hypothesis, which says that that claimed distribution is not correct. All right, so now that we've looked at an example of the type of problem we might do, let's start looking into some specifics. And so anytime we state the null and alternate hypotheses for a chi-squared goodness of fit test, we are stating that the claimed distribution for a categorical variable is correct. So then obviously the alternate would state that that claimed distribution is incorrect. So here is another way of wording what we put for our alternate and our null hypotheses. So the null says the company's stated color distribution for M&M's milk chocolate candies is correct. That is way better than what we wrote up here because it's so specific, right? And so in this case, if I'm not going to define the parameter before I state these, then I need to be very specific in my hypotheses, okay? We could also write these hypotheses using symbols. And so we could say P Brown equals, they claimed 13%. The percent of yellow is, oh man, I just looked at it, 14%. The percent of orange is 23%. I'm just going to write etc. here. And then if we copy that, our alternate would state the exact same thing, except it would state that they're not equal. So the percent of brown is not 13, the percent of yellow is not 14, the percent of orange is not 23, etc. Now, more often than not, like always, I use this type of format. for our null and alternate hypotheses, because sometimes you've got so many categories in a distribution that you have to list them out. But I wanted you to notice we could reword them using those symbols like we did down below here, so that we're saying the exact same thing. All right. Now we're going to talk about the conditions. So instead of 2 conditions, we actually have 3. I mistyped there. Our first is random, so the data must come from a random sample or a random experiment. We must have large counts, so all expected counts are at least 5. That comes from having a large sample size. So if we come up here, our expected counts were all these numbers in the expected column. Notice all of those were bigger than 5, right? So we want to know every category will be represented by more than 5, or at least 5 units of whatever we're looking at. That's the large counts condition. And then the last one is independent. Your sample size n cannot be more than 10% of the population. Okay, so like our sample size of 100 M&Ms is absolutely less than 10% of the population of all M&Ms. Okay, so now we're going to look at a couple examples. Casinos are required to verify that their games operate as advertised. American roulette wheels have 38 slots, 18 red, 18 black, and 2 green. In one casino, managers record data from a random sample of 20 spins of one of their American roulette wheels, noting the color spun each time. They use this data to run a chi-squared test for goodness of fit. So our null hypothesis here would say that the distribution, of colors on the roulette wheel is correct. Maybe we should say the claimed distribution there. So then the alternate will say the exact same thing. I'm going to cut and paste exactly what we just wrote. Erase this. And the only difference is that our correct becomes incorrect. Okay, and so our test will be checking, is a given roulette wheel following the correct distribution of colors? Now the conditions, remember there's 3, not 2. Did we get a random sample? So the first one, random. It says we did a random sample of 200 spins, so yes. 2 is large counts. To do large counts, we would have to know our expected counts. So we can write those down below. Right? So our expected, oh my goodness.
Playing fetish on Spotify.
Our what we would get for each color given the claim distribution. So if we are looking at our claim distribution, 18 out of 38 should be red. That's our percent for red. So if I find that, it is like 47.3684, but then I'm doing a sample of 200, so I'm going to multiply that by 200. So we would say for red, we have 18 over 38 times 200. We would expect to get 94.74 reds in our 200 spins. For black, we would do the same. So I'm just going to write black here. The same. And then for green, we would have had 2 out of the 38 times the 200 spins. So 10.526, so maybe 10.53 would be black. That does satisfy large counts because all expected values are greater than or equal to 5. And then our last one, 3, is independent. And that is satisfied because 200 is less than 10% of all possible spins. All right. Moving on, in his book Outliers, Malcolm Gladwell suggests that a hockey player's birth month has a big influence on his chance to make it to the highest levels of the game. Specifically because January 1st is the cutoff date for youth leagues in Canada, where many NHL players are from. Players born in January will be competing with players who are up to 12 months older than them. The older players tend to be bigger, stronger, and more coordinated. Hence, they tend to get more playing time, more coaching, and have a better chance of being successful. To see if birth date is related to success, based on whether or not a player makes it into the NHL, a random sample of 80 NHL players from a recent season was selected, and their birthdays recorded, and a chi-square test for goodness of fit was run. Okay, so this is the second type of goodness of fit test. Notice in this test for the roulette wheel and in this test up here for the M&Ms that we talked about, they had each category represented by a different percent. But in this category, we would be checking to see in this sample of NHL players, is every month represented equally when it comes to birth month? So our null hypothesis would say every month is equally represented for birth months of NHL players. Then the alternate would be the exact same. I'm going to run out of space, aren't I? Yikes. I'll just write it and then shrink it down. Would be not equally. So So what that would be proving is that these months, some players, months are not equally represented, I guess. And so you've got a higher percent of players born in March than you do in other months, and so on and so forth. Our conditions here, random. Yes, right, they took a random sample of 80 NHL players. Expected counts. Well, it's large counts, I guess, is the actual condition, but we have to use our expected counts. Would be checked off, and let's talk about why. So here, we would expect every month to be represented. So here, if I write expected. Oh my goodness. In this case, because we would expect that null hypothesis to be true and every month to be equally represented, then every month would represent 1/12 of the 80 players. 1/12 times 80 is 6.67, which is absolutely greater than or equal to 5. So yes, we can check off our large counts condition. And then independent, that is checked off because 80 is definitely less than 10%. of all NHL players. All right, and so that shows you this goodness of fit when we're checking the accuracy of a given distribution. That distribution could either be divided up using different percentages, like the different colors of M&Ms or the different colors on the roulette wheel, or it could be divided up into categories that are equally represented. For example, this birth date. And I think I gave you one of each type in the exit ticket. So see how you do on your practice, and we'll check in tomorrow with another day of chi-square tests.